Now we'll discuss the polar curves r is equals to f of theta. Okay, this is the polar equation. Now before that, we'll see the representation of this polar coordinates. As all of you know, the transformation from Cartesian to polar, x is equals to r cos theta and y is equals to r sine theta, okay, where r and theta are polar coordinates. So here you draw any line in any direction. That line is said to be an initial line whose angle theta equals to 0 with itself. Okay. Then draw the line perpendicular to this initial line, so which is represented by theta equals to pi by 2. Then draw a line which is at 180 degree to the initial line, which is given by theta equals to pi, and the line which is in opposite direction of theta equals to pi by 2 and which is given by theta equals to 3 pi by 2. So here there are infinite number of lines which are passing through this origin. So equation of this line is given, equation of all these lines given by theta equals to alpha. So you know theta is angle between this initial line, that is said to be an x-axis. This is your x-axis, and r is the distance of the point from the origin. Distance of the point from the origin. So this point is represented by r comma theta, right? R is the distance of this point from origin. So here origin in polar form is said to be pole. Okay, so this is your pole. So here equation in polar form is represented by r is equals to f of theta. So if for theta equal to 0, suppose your r is a, so that point will be represented here, that a comma 0. So for theta equals to 0, r is a. Suppose for theta equals to 0, r is minus a. So what does it mean? Distance of the point from the origin, distance of the point from the origin on the line theta equals to 0 but in negative direction. Okay, so distance, you know, it's an absolute value. So distance is a comma 0. So r is negative of a means what? Distance from the origin in negative direction. So this is minus a comma 0, right? But the same point can be represented as a comma pi, because this point is on the line theta equals to pi in positive direction. So you can denote it by a comma pi. So in this way we'll represent these points r theta on this polar coordinates. So we'll see the rules to find out the curve, polar curve r is equals to f of theta. So say the first rule is about symmetry. Okay. So by changing theta to minus theta, if equation of curve remains unchanged, then the curve will be symmetrical to the initial line theta equals to 0, that is x-axis. Second, if we replace r by minus r, And if equation remains unchanged, then the curve will be symmetrical to the pole. That is symmetry in opposite quadrants. So this symmetry will be obtained by replacing r by minus r in the equation. If equation remains unchanged, then we'll say that curve is symmetric in opposite quadrants, or it is symmetric to the pole or origin. Third, if we replace theta by minus theta and r by minus r simultaneously, if equation of the curve remains unchanged, then the curve is symmetrical about y-axis. See, the same symmetry can be obtained. So sometimes after changing theta by minus theta and r by minus r, equation may change. So it doesn't mean that it will not symmetrical about y-axis. So in that case, we'll check this another rule for the same symmetry. So in that, we'll replace theta by pi minus theta. If equation remains unchanged, then we can say curve is symmetrical about y-axis. Right? So these are the rules about symmetry. Now second rule is about the origin, or you can say pole here in polar form. Okay, so here we'll check whether value of r is 0 for some values of theta. Okay. If it is, then we can say that curve will pass through pole or origin. So once the curve passes through pole or origin, it is necessary to find out the tangent at origin. So to get the tangent at origin, there's a simple rule. Substitute r is equals to 0. The value of theta gives the tangent at pole. Right? So actually these two are similar. So if for some value of theta that r is 0, okay, for some value of theta, if that r is 0, it means that curve will pass through pole, and that value of theta means that theta will be the tangent to the pole. Now third rule, prepare the table of values of r for some values of theta like this. So theta r. So we'll consider some values of theta and we'll find out the values of r. It will help you to trace that polar curve there. Okay. And rule 4 is the region of absence of curve. So see here, your equation is r is equals to f of theta. Okay. So here theta varies from 0 to 2 pi, right? Theta will varies from 0 to 2 pi always. So for some values of theta, for all the values of theta, you will have maximum value of r and minimum value of r there. So see, first rule about region of absence of the curve. Now see here, your nature will be like this. Initial line theta equals to pi by 2, theta equals to pi, theta equals to 3 pi by 2, and there might be infinite number of lines in between these. So if we consider this one as a nature, suppose, so what we are observing here, see, you will get points like this. Okay, distance of the point from the origin on the line theta equals to 0, then theta equals to a, theta equals to b, and so on. So you'll get points like this, right? So what you are observing here, we are getting the space between theta equals to 0 and theta equals to a, or theta equals to a, theta equals to b. We have some space there. So this space is said to be in sectors. So these are the sectors actually. Okay. So here we'll check the region of absence of the curve in these sectors. Whether curve exists in this first sector, whether it exists in second sector or third sector, or if we have say theta equals to 0 to theta equals to pi by 2, these two values only. So we'll take in between any value of theta. Okay. If r square is negative or r is imaginary, for some values of theta, say theta equals to alpha and theta equals to beta, then no branch of the curve will exist between the lines theta equals to alpha and theta equals to beta. Here, say for example, between these two lines theta equals to 0 and theta equals to a, if I take theta equals to say alpha, okay, and if value of r is imaginary for this theta or r square is negative for this theta, then no branch of the curve will exist between these two lines theta equals to 0 and theta equals to a. So this is how to check the region of absence of curve here by this first rule. Now second, say r is equals to f of theta. As I said, your maximum value of r, suppose say a, for some values of theta, then the curve will not exist beyond a circle of radius a, or curve will exist inside the circle of radius a. So it is quite obvious, if r is maximum r if we get, then all other values of r will be less than that. So your curve will be within the circle of radius a. So that we'll see in examples. So these are the rules. Okay. So again, I'm repeating. See, symmetry, replace theta by minus theta. If equation remains unchanged, then curve is symmetrical about x-axis, or you can say about initial line theta equals to 0. If we replace r by minus r, equation remains unchanged, then curve will be symmetrical to the pole, or you can say symmetry in opposite quadrants. If we replace both theta and minus theta by minus theta and r by minus r simultaneously, and if equation remains unchanged, then the curve will be symmetrical about y-axis, or same symmetry can be checked by replacing theta by pi minus theta. If equation remains unchanged, by changing this theta, then curve will be symmetrical about y-axis. Second, pole or origin. So what you're going to check for some value of theta whether r is 0. If it is 0, then curve will pass through the pole, and that value of theta will be the tangent at pole. Or you can simply substitute r is equals to 0, and you can check whether we are getting some theta or not. If we are getting some theta, then we can say curve is passing through pole, and that value of theta will be tangent at pole. Third, we'll prepare this table. So I'll tell you later which values of theta is to be considered there. Okay. A region of absence, as I said, r square is negative. Suppose for some values of theta, say alpha and beta, then no branch of the curve will exist between these two lines, theta equals to alpha and theta equals to beta, right? So I'll explain it while discussing the examples. So first example, r is equals to a into 1 plus sine theta. Okay, so we'll go through the rules. So rule 1 is about symmetry. So if I replace, so first rule we'll check, if I replace theta by minus theta, I'll get sine minus theta as minus sine theta. So your equation remains changed. Equation is changing here. Therefore, curve is not symmetrical about initial line. Second, if I replace r by minus r, then my equation is changing. So curve is not symmetric to the pole, means symmetry is not there in opposite quadrants. Okay. So third, we'll replace r by minus r and theta by minus theta simultaneously. So we'll get minus r here, a 1 plus sine minus theta is minus sine theta. So we'll get minus r equals to a into 1 minus sine theta. So equation is changing. So here you do not conclude immediately that curve is not symmetrical about y-axis. we'll check the equivalent rule for this symmetry, okay, and that is replace theta by pi minus theta. So if we replace theta by pi minus theta, we'll get r equals to a into 1 plus sine pi minus theta, right? And what's a sine pi minus theta? Sine pi minus theta is sine theta. Pi, that's why sine as it is theta, and pi minus theta means second quadrant where sine is positive. So you'll get r equals to a into 1 plus sine theta. So equation remains unchanged by changing theta by pi minus theta. Therefore, curve is symmetrical about y-axis. You can see, okay? Curve is symmetrical about y-axis. Now, rule 2 is about pole, or you can say origin. So we'll check whether this r is 0 for some values of theta or not. So here r is 0 for theta equals to 3 pi by 2. See, sine 3 pi by 2 is minus 1. Sine pi by 2 is 1. Sine 3 pi by 2 is minus 1. Sine 5 pi by 2 is 1. Sine 7 pi by 2 is minus 1, and so on. Right? So here for theta equals to 3 pi by 2, this r is 0. So here r is 0 for theta equals to 3 pi by 2, and therefore curve pass through pole, right, or origin, you can say. Now since curve is passing through pole, so we'll find out tangent at pole. So to get tangent at pole, put r equals to 0 in the equation of curve. In 1, you can say, let this equation be 1. Okay. So put r equals to 0 in 1. So what we'll get? A into 1 plus sine theta equals to 0, which implies sine theta equals to minus 1, which implies theta equals to sine inverse minus 1, which is 3 pi by 2. So is it 3 pi by 2 only? So inverse sine function is multivalued function that we know. Okay. So sine inverse of minus 1 is 3 pi by 2, as well as I said just now, for 3 pi by 2 it is minus 1, 5 pi by 2 it is 1, 7 pi by 2 it is minus 1 again. So this is 7 pi by 2. Then for 9 pi by 2 it is 1, for 11 pi by 2 it is minus 1, and so on. So these are the tangents at pole, tangents at origin. So let us see this curve. So we'll draw it simultaneously. So this is theta equals to 0, theta equals to pi by 2, theta equals to pi, and theta equals to 3 pi by 2. So curve is passing through